Okay, physics, let me talk you through some of these questions and what I think the answers are to them. So I haven't worked out these beforehand, so let's figure it out. So first one, I'm going to rank the slopes of the graphs and label points, right? So trick one, this is that A is going to have a negative slope, so I'm going to rank these from most positive to most negative. So I'm thinking D is going to have the greatest, followed by C, which is equal to B, and then A is going to be the lowest slope. So if this was a physics graph, we'd have a negative slope on one of those. Similarly, we're going to start looking at instantaneous slopes. So we're looking at a particular point on the line, find the instantaneous slope. So I want to find a tangent line for that. So easiest way to do this, I'll make a ruler, put my pencil there, and try to draw a line so that that line touches that slope only at one point. There it is. There it is. There it is. And there it is, right? So this is my tangent line, and this is essentially what calculus is going to tell us. So when we get into derivatives, it's going to tell us essentially what is the rate of change at a particular point in time. And graphically, how we do this is with the tangent lines. So now I have the same problem. I'm going to rank the slopes. Again, I have a negative slope, positive slope. So I'm going to have D, which is going to be the greatest, followed by C. And then I'm going to have B, which is 0. And then A, negative, is going to be less than 0. So hopefully I came up with something that looks like that. Moving on. So what's wrong with the statement? So I'm looking at a graph here, and I'm hoping that you recognize that this axis is really expanded, unusually so. So the difference between 5,040 and 5,080, right? Not super significant, but a common thing to do with graphs is try to blow these up. So hopefully you're getting comfortable with that. Grown dramatically? No. Grown? Well, sure. And, rest of it's interpretation of the situation. Okay, starting to get into motion graphs with physics. So, cat's moving away from sleeping dog on a hallway. The graph of the distance of the cat from the dog is a function of time. The student uses the equation rate times time equals distance, right? So this is the definition of velocity. It's going to be my change in distance over time. And if I rearrange this, so my velocity times time is going to be the distance or displacement that's occurred during that time frame. Calculus speed. So right, what's wrong with this? So the key thing here, right, is that remember this is the rate is the change in distance over time, or the slope of this, right? So the slope is telling me velocity. Slope equals velocity. And notice I have two different slopes, therefore two different velocities, right? So the cat sped up, so he got 5 meters or 5 seconds away from the dog, right? So this calculation is only true when we have constant velocity, right? And we can use it for average velocity if I have constant acceleration, but this is telling me if I have constant velocity, and we're going to have the same thing. So we're going to have acceleration, and under constant acceleration, we're going to have one equation, and if it's non-constant acceleration, all bets are off, and you have to use something else, calculus. So anyway, hopefully you're starting to recognize, so it's really important that you get the distinction between sort of an average velocity, the constant velocity, and then an instantaneous velocity, and they can all be different things at different times. A few questions, information from the graph. So what's the average acceleration? So now I'm on a velocity time graph. So the slope from this is telling me acceleration. So here my acceleration is 0. Here my acceleration is 0. Here my acceleration is 0. So my average acceleration between 0 and 6 seconds, right? So my average is going to be my change in velocity over time, right? Doesn't matter how I went there. If I'm looking at the average, like you're driving a long distance and you stop along the way and you get gas, or you go to a restaurant, whatever. But the average is going to be the total distance over the total time for velocity, and the same average is going to be true for acceleration. It's going to be the total change in velocity over the total time. Right, so I'm going to be my v final. So it's going to be final minus v initial divided by time, and I'm going to end up at 0. I had initial velocity of 3. I'm going to subtract that from my final velocity at 6 seconds, which is 6 divided by 3. So I'm going to get 0.5 meters per second squared. Hopefully you got something close to that. Acceleration of the object at 1.0 seconds. So 1.0 seconds. So in here it's asking me what is the slope of that line there, right? So what's the rate of change of velocity? So I don't know. So my acceleration is going to be my change in velocity over my change in time. So I'm going to pick a section here. So I'm going to just go from this point to figure out what my slope is. So my change in velocity, I start at 2 and I go to 0. And that takes me 1 second. So my acceleration is -2 meters per second squared. Negative sign is really important. Distance traveled between 0 and 4.5 seconds. So, yeah, distance traveled. A couple ways to go about this. One way is I can find this area under the curve. Remember, so if I'm on a velocity time graph, the slope tells me acceleration. The area under the curve tells me the displacement, or the I have to be careful though. So this is sort of a tricky question here. So they're asking for distance traveled, not displacement, right? So I want to be careful here. So here I travel a distance which is going to be in the positive direction, and then I travel a distance which is going to be in the negative direction. My total displacement from where I start to where I end is not going to be that far, but the distance traveled, I've traveled there and back, is going to be further. So what I want to do is first I'm going to figure out, what's the area under these. So I'm going to count squares: 1, 2, 3, 4, 5, 6 whole squares, plus 1/2, 2/2, 3/2. So it's got 7.5 squares. So distance traveled. So in the positive direction, I'm going to have 7.5 squares. So each square is what, half a second times 1 meter per second. Right. And notice my units come out to meters, so basically I'm going to take half of this. So I've traveled in the positive direction 3.75 meters. Now I want to figure out how much I traveled in the negative direction, so I'm going to count squares. I've got 1, 2, 3, 4, 5 whole ones. I'll call this 6. I'll call this 7. So I've got 7 whole ones in the negative direction. And again, each square is 0.5 seconds times 1 meter per second. So I'm going to end up with 3.5 meters in the negative direction. Is asking for the distance traveled. If it's asking for the displacement, I would subtract these two, because one's the positive direction, one's the negative direction. Distance traveled, I'm going to add these two together. I'm going to get 7.25. I'm going to get 7.25 meters is the distance that's been traveled. Trick question. Displacement. So displacement between these two, now I'm going to subtract this. So I go 3.75 in the positive direction, 3.5 in the negative direction, so I end up 1/4 of a meter away from where I started in the positive direction. Average velocity over the entire time interval. Well, my average velocity is going to be my change in displacement over time. It doesn't matter how I got there. So I already know the displacement for these two areas, so let me figure out the displacement for these other things. Right? So this is what I'm thinking. I'll just figure out what's the area under the curve for these, which is going to tell me the displacement. So for this area, I got 3.75 meters. For this area, I had 3.0 meters negative. For this area, what's that? 1, 2, 3, 4, 5, 6, 7, 8. Call it 9. Half of 9 is 4.5 meters. In this area, I've gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. times 0.5 times 1, which is going to be 9, 0 meters. And this one I've gone, oh good grief, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17 and a half. And then again, I'm going to multiply it by half a second and 1 meter per second. Good grief, what did I say? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and a half. 17 and a half. Half of 17 and a half. 8.75. So my total displacement is going to be 3.75 minus 3.0 plus 4.5 plus 9.0 plus 8.75. So I got a quarter, so 9, 18, 22.5. So I'm thinking this is going to be about 22.5 meters is how far you've gone. And it took you 10 seconds to do that. So my average velocity is going to be 22.5 divided by the 10 seconds that it took you to do that. Right, so I'm going to end up with 2.25 meters per second positive. Graph the position versus time. Oh, great. Right, so same idea. So I know in the first 1 second, where have I gone? So I've gone first half a second, I've gone 3, I've gone 1.5 meters. So I don't know, I'm going to assume I start at 0. You don't know where you start, it could be anywhere. So I'm going to make this, oh good grief, I'm going to end up 22.5 meters away. Right? So to make this graph work, I'm going to end up being 22.5 meters away. So the top here, I don't know, let me make my scale work. So 1, 2, 3, 4, 5. So I'm going to call this 25. That's 20. This 15. This 10. This 5. These are meters away. So in the first half a second, I'm going to go at a constant velocity, and I'll be 1.5 meters away. So I don't know, I'm going to be over here someplace. I'm going to draw a straight line. Up at 2 seconds, from that point to 2 seconds, I travel an additional 3.75 meters in the positive direction. Or sorry, 2.75. So I end up at 4 meters at 2 seconds. So I end up here. So I slowly increase to 4. Now I get to 0 velocity. And now I'm going in the opposite direction. So between 2 and 3 seconds, I'm going to go in the opposite direction. What's this? 2 squares, which is going to be 1 meter. Right? So 1 second. Yep. So 1 second, I'm going to go back 1 meter. Not very much. And then for the next second, I'm going to go back 2 meters. So I'm at 4 seconds now. Yep, so I'm going to get to 4 seconds. I'll get there. And then for the next half second, I'm going to go backwards half a meter, right? So I get really close. Remember, I get 0.25. I don't go negative, right? So at this point here, this is the displacement, total displacement. I've gone positive 3.75, and I come back 3.5, and now I'm going to take off in the other direction. So from 4.5 to 6 seconds, I gained 4.5 meters. So 4.5 to 6, I'm going to be pretty close to here. So I'm going to draw a line. From 6 to 7.5, I go 9 meters. So now I'm up to 13. So 6 to 7.5, I'm going to be at 13. Up here, call it. And then at for the last 7.5 to 10, I'm going to go at 8.75 an additional 8.75, so I'll get to my final 22.5, which is going to be up here, right? So technically, whenever I have a flat line on velocity, I'm going to have a straight line on my displacement, and wherever I have a sloping line, I'm going to have some sort of curve. Remember, so here I'm having negative acceleration, so I'll have some part of a frown. Here I have positive acceleration, I'll have some part of a smile. Right, so it is, yeah, imagine, this should be a curve, this should have some curve in it, this should have some curve in it, this should have some curve in it. Really subtle and hard to make out in this one. Anyway, I hope you got something close to that. If not, I hope it's helpful, and talk to you soon. Bye.